Hello everyone, welcome to our channel Knowledge of Friends. Subscribe to our channel and click the bell icon for the latest update. आज हम लोग केमिस्ट्री की क्लास करने वाले हैं. केमिस्ट्री की क्लास जो भी 144th क्लास है, ऑलरेडी हमने 143 क्लासेस कर लिया है एंड जिसमें हमने यूनिट 1, यूनिट 2, यूनिट 3, यूनिट 1 की बात करते हैं अगर हम, तो यूनिट 1, यूनिट 2, यूनिट 3, यूनिट 4, यूनिट 5 और हम जो कर रहे हैं यूनिट 6 कर रहे हैं जो कि थर्मोडायनेमिक्स है. थर्मोडायनेमिक्स में हमने थर्मोकेमिकल इक्वेशन से पहले जितने भी टॉपिक्स थे वो कवर अप कर लिए हैं. आज जो हम डिस्कस करेंगे वो थर्मोकेमिकल इक्वेशन को डिस्कस करने वाले हैं. फर्स्ट ऑफ ऑल, अगर आप हमारा चैनल फर्स्ट टाइम देख रहे हो या अभी तक आपने हमारे चैनल को सब्सक्राइब नहीं किया है, इट्स अ ह्यूज रिक्वेस्ट कि आप हमारे चैनल को सब्सक्राइब करो सो दैट हम जो भी वीडियोस डालें वो आपके पास सबसे पहले पहुंचे. एंड सेकेंडली, अगर आपको हमारा वीडियो अच्छा लगे तो प्लीज़ हमारे वीडियो को लाइक, शेयर और सब्सक्राइब करो सो दैट ज़्यादा से ज़्यादा लोग के पास वीडियो पहुँचे, ज़्यादा से ज़्यादा लोग इसका यूटिलाइजेशन भी कर सकें. Now, in terms of that thermochemical equation and static enthalpy that we'll discuss here in this class, and that we have to start with the thermodynamics, thermochemical equation in the thermodynamics here. So here the D.O will be the thermochemical equation. In terms of the thermochemical equation, a balanced chemical equation together with the value of its delta of R of H is called a thermochemical equation. अगर हम balanced chemical equation के रिस्पेक्ट में बात करते हैं तो हम जब दोनों को डेल्टा आर एच को एक साथ लेते हैं तो वो हमें थर्मोकेमिकल इक्वेशन प्रोवाइड करता है. In terms of the provision of equation that it provides, we specify the physical state along with the allotropic state and that of the substance in that equation. And like for example, we'll take C2H5OH, and that is in the form of liquid state, plus 3O2 that is in the form of gaseous state. When they combine in the form of a reactant, then they give us product 2 carbon dioxide, that is CO2 in the gaseous state, and 3H2O that is in the liquid state here. इनका जो डेल्टा आर एच सब्सक्रिप्ट है वो -1367 किलो जूल मोल इनवर्स है. ये माइनस साइन जो है वो आपका शो करता है कि जो ये रिएक्शन है वो एक्सोथर्मिक रिएक्शन है. ऑलरेडी मैंने इसी लेक्चर में बहुत बार आपको ये चीज़ बताई है. एक्सोथर्मिक रिएक्शन है जिसकी वजह से जो क्यू भी होगा, अगर हम क्यू हीट कैपेसिटी निकालते, हीट एब्जॉर्ब निकालते, तो वो भी आपका निगेटिव ही होगा क्योंकि एक्सोथर्मिक रिएक्शन है. With this reaction, the above equation described to the combustion of that liquid of ethanol and that constant temperature and pressure, where the negative sign of an enthalpy change indicate that this is an exothermic reaction, as I told you here also. With reference to that, it would be necessary to remember the following convention regarding thermochemical equation, that the necessary to remember that following convention that is regarding to the thermochemical equation. So these were the three the conventions regarding this thermochemical equation. The first convention we have is the coefficient in a balanced thermochemical equation. अगर हम coefficient of balanced thermochemical equation refers to the number of moles, never molecule of reactant and particles involved in the reaction. जो coefficients होता है balanced thermochemical equations के, वो आपके basically refer करते हैं number of moles पे, ना कि molecules के number of moles पे refer करते हैं, and that is of the reactant as well as the product that is involved in that particular reaction here. While in terms of talking about the second one, that the convention that we have here is the numerical value of delta R of H subscript referred to the number of moles of substance specified by an equation, that is a standard enthalpy change, that is delta R H of subscript here, that will have a unit as a kilojoule or mole inverse. To illustrate this concept, let us consider the calculation of heat reaction of the following, that is Fe2O3 that is in the form of solid state plus 3H2O that is in the form of gaseous state. It gives 2Fe that is in the solid state and plus 3H2O that is in the liquid state here. From this that what we had discussed about the table, that the standard enthalpy of the formation, that is of delta F of H subscript, that we'll find it out with respect to that. From that table we'll take it out from the Fe also, and that is delta F H subscript is H2O that is in the liquid here, and then that is equals to, from that table अगर हम बात करते हैं तो आपका यहाँ पे दिया हुआ है, अगर वो टेबल आपने नोट किया है तो होपफुली यू विल गेट टू नो कि वो क्या है एक्चुअली में. डेल्टा F फ्यूजन दैट H सबस्क्रिप्ट जो H2O का लिक्विड स्टेट में था वो -285.83 किलो जूल मोल इनवर्स था, और डेल्टा फ्यूजन जो आपका H सबस्क्रिप्ट Fe2O3 का सॉलिड स्टेट वाला था दैट इज -288 किलो जूल मोल इनवर्स, जो कि मैंने आपको इसीलिए पहले टेबल बताई थी जिसकी वजह से आपके लिए कैलकुलेशन थोड़ी सी ईजी रहे। एंड ऑल्सो डेल्टा एफ ऑफ एच सबस्क्रिप्ट दैट इज Fe जो कि सॉलिड स्टेट में था दैट इज 0, and that S subscript of H2 gas that is also 0 per conventions here. Okay, so and with this then we'll find it out the delta RH of, and then delta RH 1 subscript equals to 3, and that is multiplied 3 यहाँ पे था तो इसलिए 3 multiplied by Fe that we have here is 3, and here 3 and H2O हमारा जो था that is -285.83 and kilojoule mole inverse, then minus 1 यहाँ पे and 824 यहाँ से आया that is of Fe2O3, and Fe2O3 that is multiplied, and of course then we'll get 1 here, and this will be multiplied by this, then we'll get -835.75 plus 824.2. when we multiply this then we'll get 857.5. A5 we just multiplied here, and according to 3 3s are 9, and then 3 8s are, and then according to that we'll just take our first decimal place because it has a after decimal this is a one place value, so that's the reason we had taken this one also as a single one placed value, 1th place value. Then we add on this 5 plus 2 that is 7 here, and then after that 7 plus 4, then after that 5 plus 2, and then 8 plus 8, then after that we'll get here is this is minus and this is plus, so plus minus minus hota hai, so we'll just subtract it out and find out 33.3 kilojoule mole inverse here. Okay, so with respect to this after solving this, after finding out this when we have -33.3 kilojoule mole inverse, you will also note that the coefficient that is used to for the calculation are a pure number where which are equals to the respective stoichiometric coefficient, and the unit of the delta RH is that is a kilojoule mole inverse, which means that per mole of the reaction, once we balance the chemical equation in a particular way as we had done, that defines the mole of reaction. If we had a balance in the equation differently, for example like if we balance this half Fe2O3 that is in the form of solid state plus 3/2 H2 that is in the form of gas state, and that is gives the product Fe that is in solid plus 3/2 H2O that is in the space of liquid here. So then the amount of the reaction would be 1 mole of the reaction, that is of delta R of H subscript would be, and that is delta R of H2 subscript is 3/2, and bracket the values -285.83 kilojoule mole inverse, and then -1/2, then -824.2 kilojoule mole inverse. While solving these two equations here, we will get, while solving this we will get here is -428.7 plus, and then we have this that is 412.1 kilojoule mole inverse here, as well as यहाँ पे माइनस है और यहाँ पे भी माइनस है, तो माइनस माइनस जो होगा वो यहाँ पे आके प्लस हो गया, and this is only the single minus, so we'll just do write it here, minus plus minus होता है, so we'll just subtract it out for 428.7 minus 412.1 kilojoule mole inverse, so we'll find it out minus 16.6 kilojoule mole inverse, that is equals to 1/2 delta R H1 as of subscript here. Okay, after that the third convention for regarding the thermochemical equation we have is N2, that is in the form of gas state, plus 3H2, and that is of gas state, and that gives 2NH3 that is in the form of gas. Delta R H subscript equals to -91.8 kilojoule mole inverse. We have 2NH3 of gas state, we have N2 gas, and plus 3 H2 that is in the form of gas state, and we are delta R of H subscript that is equals to plus 91.8 kilojoule mole inverse. Here when we are if it's conclusion that the convention that we have here is that it shows the enthalpy is in extensive quantity, that it shows the extensive quantity. And now for this, as what we had recognized, when a chemical equation is reversed and the value of the delta RH is reversed in the sign, and for example, like we had taken this delta R of H subscript that is equals to minus 91.8 kilojoule mole inverse, where 2NH3 of gases that gives the N2 in the form of gases plus 3H2 and that is in the form of gases. So delta RH subscript will get plus 91.8 kilojoule mole inverse. If we reverse the equation, जैसे कि N2 और 3H2 से वो NH3 बन रहा था, तो हम NH3 से अगर N2 और 3H2 बनाएंगे, so what will reverse the equation, so the sign जो होगा वो चेंज हो जाता है, नेगेटिव है तो पॉजिटिव हो जाएगा. This is what the third convention states that. Okay, now we'll deal with the Hess laws here, and Hess law of a constant Hess summation, and what we'll discuss here, and Hess law of the constant heat summation we will discuss here. In reference to the Hess law, that is constant of the heat summation, before starting with this, we know that the enthalpy is a state function, therefore the change in the enthalpy is independent of the path between an initial state, that is reactant, and the final state, that is product. In other words, enthalpy change for a reaction is same whether it occurs on a one step or in the series of the steps. This may be stated in the follows in the form of the Hess laws, and the Hess law states that if a reaction take place in several steps, अगर reaction जो है वो आपका several steps में take place कर रहा है, then its standard reaction enthalpy is the sum of the standard enthalpies. जो आपका reaction enthalpies होगा, standard enthalpy वो sum of होगा of the intermediate reaction into which the overall reaction may be divided at the same temperature. Let us understand that importance to by this law, that the help of consider the enthalpy change for that particular reaction. We have a C that is in the form of graphite here, and that is solid, half O2 and gas that gives the delta of G, and CO that is in the form of the gaseous state, and where we don't know that delta R of H subscript, we have to find it out. We don't know about this. Now, with reference to this, although the carbon monoxide here, that is in the form of a gases, is the major product, some carbon dioxide gas is always produced in this reaction. Therefore, we cannot measure enthalpy change for an above reaction that directly. How if we can find it out some other reaction involving the reactants that is related to the species, it is possible to calculate the enthalpy change for that particular above reaction here. With reference to that, we have another equation with reference to the graphite only, that is a C graphite that is in the form of solid state, and plus O2 here, and that is in the form of the gas state, that gives the carbon dioxide that is in the form of gas state, where we will find it out the delta R of H subscript, that is your minus 393.5 kilojoule mole inverse. And with respect to that, we can just discuss the carbon monoxide gas plus a half O2, and then we'll get carbon dioxide that is in the form of gas state here as well, and the delta R of H subscript is equals to minus 283.0 kilojoule mole inverse. We can combine the equations, these two equations in such a way that to obtain the desired reaction to get 1 mole of carbon monoxide gas of on the right, and we reverse the equation, and this so heat is absorbed instead of being released, so that the change of the delta RH value will be the change here. Okay, so we can go through with this. So here you can see that carbon dioxide that is in the form of gaseous state, it gives the carbon monoxide plus half of HO2 that is in the form of gaseous state. So delta R of H subscript will get here is plus 283.0 kg, that is kilojoule mole inverse here. Adding these equations, that we will get a desired equation, that is C graphite plus we have C graphite plus half H2 half O2 that is in the form of gaseous state, that gives a carbon monoxide, and that is in the gaseous state. Your delta R of H subscript is equals to minus 393.5 जो कि हमारा आया था plus 283.0. we will add on these minus plus minus होता है, तो we'll just 393.5 में से 283.0 minus करेंगे, we'll get 5 में 0 गया तो 5 ही बचेगा, and this is 3 and this is 3, 3 में 3 गया that is 0, 9 में 8 गया बचेगा 1, and 3 में 2 गया बचेगा 1, क्योंकि बड़ा साइन नेगेटिव के साथ है तो इसलिए नेगेटिव साइन लगेगा. तो we'll get delta R of H for this equation is minus 110.5 kilojoule mole inverse. Okay, So where we in general, if the enthalpy of an overall reaction A to B, this is reactant and this is of course a product here. Along one route is delta RH and delta RH OH1 and delta RH to H2 and delta RH3 and so on till the delta nth of nth Hn, representing the enthalpies of the reaction leading to the same product B along with any another route. Then we have here, as you can see, that the delta RH equals to delta R of H1 plus delta R of H2 that plus delta R of H3 plus delta R H4 and delta R plus H5 and so on till the delta nth of H nth. Okay, delta R of H nth, we will be adding on all these and we will find out delta R of H here, where it can be represented in the form of this particular figure that we had represented here, so that you can understood in an easy way here. With reference to that, A है आपका, जो A आपका डेल्टा आर एच जो B में गया, so here A से फिर ए सी में गया डेल्टा आर एच वन एच गया और एच वन भी इधर से गया सी में, सी से फिर डेल्टा आर एच टू गया फिर डेल्टा आर एच थ्री गया. इससे क्या होता है, जन वी फाइंड आउट डेल्टा आर एच हियर, सो वील जो कैन ऐड अराउंड डेल्टा आर एच वन डेल्टा आर एच टू डेल्टा आर एच थ्री एंड प्लस एंड सो जितने भी पॉसिबल बनेंगे. सो यू कैन जस्ट ऐड एंड ऑन, यू कैन फाइंड डेल्टा आर एच what it transfer from one place to another here. Now with respect to that, we have another heading that we have to discuss here, and that is enthalpies for the different types of reaction. कि different types of reactions में क्या enthalpies होती हैं, क्या देखने को मिलती है, that enthalpies for the different types of reaction. So the first heading for this is standard enthalpies of combustion. Standard enthalpies of combustion जो देखने को मिलती है, like symbol is delta R H subscript. This is the symbol of the standard enthalpies of the combustion here. It is convenient to give the name of the enthalpies specified the types of the reaction and the standard enthalpies of the combustion, that is symbol delta R H of subscript here. With reference to that, the combustion reaction is an exothermic in nature. जो combustion reaction होती है वो आपकी exothermic nature में होती है. These are the important in industry. ये जो कि आपकी exothermic reaction होती है वो industry के purpose से important भी होती है. And a reference to the rocketry and the other walls of life, if I'm talking about the rocketry है या फिर और other जो हम उसकी बात करते हैं works of life के बारे में. Like standard enthalpy of the combustion is defined as the enthalpy of the combustion is defined the enthalpy change per mole, जो कि आपका enthalpy standard enthalpy of combustion state कहता है कि जो enthalpy change होता है per mole और per unit amount of the substance when it undergoes combustion and all, जब आपका यह combustion process में जाता है और and all the reactants in the product being in their standard state at the specified temperature, then these standard enthalpies of that combustion will be known as. Okay, so where the reactants and the product being in the standard state at the specified temperature. Now with respect to that, moving ahead, that cooking gas and cylinder, जो cooking gas हमारे cylinders में होती है, that contain mostly butane, जिसमें butane ज़्यादा पाया जाता है, that C4H10. During the complete combustion of 1 mole of butane, that is 2658 kilojoule of heat is released. We can write the thermochemical reaction for this. जब आपका butane जो कि C4H10 है वो आपका जब at butane that 1 mole of आपका 2658 आपका रिलीज हो जाता है, हीट रिलीज हो जाती है, तब हम इस एक उस केमिकल इक्वेशन को लिख सकते हैं कि C4H10 that is butane here, C4H10 in the gaseous form, and that is 13 by 2 O2 gas, and then it gives 4 carbon dioxide in the gaseous form, 5 H2O in the liquid form. Then delta R of H subscript equals to minus 658.0 kg inverse. This minus sign states that the reaction is exothermic in nature, exothermic reaction. Similarly, according to this, we can say that similarly that the combustions of the glucose, okay, combustion of glucose given out is 280 2802.0 kilojoule mole inverse of heat, for which of the overall equation, or we can just balance it out in the form of the glucose here. That is C6H12O6 here, and that is in the form of gas state, plus 6O2 that is in the form of gas state, and it gives the product here, that is 6CO2, or that is in the form of gas state, plus 6H2O that is in the form of liquid state, and that is delta R of H subscript minus 2802.0 kilojoule mole inverse. Now, with respect to that, our body also generates energy from food by the same overall process as combustion, although the first product are produced after a series of complex biochemical reactions, that is involving the enzymes here. Now we'll deal with the questions here, and that is the question for the session with reference to the enthalpies of the different types of reaction in the terms of the standard enthalpy of the combustion. That we'll find it out in this question, and this is the question is the combustion of 1 mole of benzene. एक combustion आपका जो 1 mole of benzene takes place at 298 Kelvin, and that is at 1 atm. After the combustion, carbon dioxide gases form and the H2 are produced, and 3267.0 kilojoule of heat is liberated. तो उन्होंने बोला है कि आपका कार्बन डाइऑक्साइड और H2O फॉर्म होगा, and then they, for that after combustion, that they are produced, and that at 3267 kilojoule of heat is also liberated. You have to calculate the standard enthalpy of the formation, that is delta R of H subscript of benzene, standard enthalpies of the formation of carbon dioxide in the gaseous form and the water in the liquid form. R is minus 393.5 kilojoule mole inverse and minus 285.83 kilojoule mole inverse respectively here. So here with respect to that, the जो carbon dioxide के लिए है enthalpies of formation, that is minus 393.5 kilojoule mole inverse, and H2O के लिए जो कि liquid state में, that is minus 285.83 kilojoule mole inverse. So we'll just start off finding out, and the solution we have is the formation reaction of benzene is given as like C6 that is in the graphite state, and the 3H2O that is in the gaseous state, and it forms C6H6 that is in the liquid state, and then delta R of RH subscript we don't know, that we'll have to find out. The enthalpy of the combustion of 1 mole of benzene, when the enthalpy of the combustion take place in the 1 mole of benzene here, then C6H6 of in the state of liquid state plus 15 by 2 O2, that gives 6 carbon dioxide that is in the gaseous state plus 3H2O, and that is in the liquid state here. Delta R of H subscript equals to minus 3267 kilojoule mole inverse here. The enthalpy of the formation of 1 mole of carbon dioxide gases, that is in the C graphite here, and the C graphite plus your O2 that is in the form of the gaseous state, that gives the CO2 here, and that is in the gaseous state, and that is delta R of H subscript equals to, that is minus 393.5 kilojoule mole inverse here. The enthalpy of the formation of 1 mole of H2O that is in the form of liquid, that gives H2 that is in the form of gaseous state plus half of O2 that is in the form of gaseous state, and that gives H2O that is in the form of liquid state, where delta F of fusion that is H subscript will get minus 285.83 kilojoule mole inverse here. With regard of this, if I'm talking about the multiply the equation 6 by 3, and this will be multiplying, this will be the multiply 6, and this will be multiplied, this equation will be multiplied by 3 here. So we'll get C6, क्योंकि जब इसको हमने 6 से मल्टीप्लाई किया तो we'll get C6 that is in the form of graphite plus 6HO2 that is in the form of gas state, and then 6CO2 that is in the form of gas state. Where delta fusion of H subscript will get 2361 kilojoule mole inverse. Now multiply with this equation by 3 here. So what we'll get is 3H2 in the form of gaseous state plus 3 by 2 O2 gaseous state, and that gives 3H2O, and that is in the liquid state, where the delta fusion H of enthalpy is equals to minus 857.49 kilojoule mole inverse here. Now moving ahead with having this particular equation to solve further, that summing up the above two equation we will get it out. जब हम 6 वाली और ये वाली इन दोनों equation को sum up करेंगे, add on करेंगे, we'll get C6 graphite plus C6 graphite plus, then we get 3H2, this is 3H2 gas, then 15, this O2 and this O2 will be summed up, and that will be 15 by 2 O2 that is in the gas state, and the product also sum up, and that is 6 CO2 gases in the form of the gases plus that is 3H2O that is in the form of liquid here. So we know that delta of F fusion, that is subscript, is equals to minus 3218.49 kilojoule mole inverse. Now reversing the equation, जब हम reverse करेंगे equation को, what we will find it out, 6 carbon dioxide that is in the form of gas state plus 3H2O that is in the form of liquid state, that gives C6H6 that is in the liquid state, and 15 by 2 that is O2, and delta of fusion H subscript will get 3267.0 kilojoule mole inverse here. Adding these equations, we will get here is 6C that is in the form of graphite plus 3H2 in the form of gas plus that gives C6H6 that is in the form of liquid here, and delta fusion of H subscript will get here is a 48.51 kilojoule mole inverse. Now moving ahead, we have to discuss with reference to this, because this 48.51 kilojoule mole inverse would be the right answer. Then what we have to find it out in the terms of the enthalpy here. Now moving ahead here. So here we have enthalpy of atomization. Enthalpy of atomization हम निकालना जानेंगे, जिसमें हमें symbol है delta that is of A and that H of subscript here. In the consider the following example for the atomization of dihydrogen, that is of H2 that is in the form of gases, that and gives 2H that is in the form of gas here, and that is of delta of AH subscript here. We will get here 435.0 kilojoule mole inverse here. With this you can see that atoms that are formed by breaking the H bond here, and that will be in a dihydrogen, and that the enthalpy change in this process is known as the enthalpy of atomization, where delta of A and that is subscript, it is enthalpy change of the breaking 1 mole of the bonds completely to obtain the atoms in the gas phase, where in the case of the diatomic molecule like dihydrogen, that is given above as what we had discussed here, is the enthalpy of the atomization, that is also bound dissociation enthalpy of the other examples of enthalpy of atomization that can be, we can just write it out in the form of that CH4 that is in the form of the gases, and that gives the carbon in the form of gases, and plus 4H in the form of the gases, and that delta of atomization, enthalpy of atomization we will get here is 1665 kilojoule mole inverse. We have to know that the product are only the atoms of carbon and hydrogen, as you can see here. Okay, and these were the hydrogens and gases in the gases phase we have. So we can see that the following equation with respect to the sodium here, sodium that is in the form of Na, that is in the form of solid state here, and with respect to that Na that is in the form of the gas state, and that gives the enthalpy of atomization we have 108.4 kilojoule mole inverse. In this case, the enthalpy of the atomization of the same as enthalpy of the sublimation here. Okay, now moving ahead with the bond enthalpy, and that what we have to discuss here. In reference to the bond enthalpy is your E part here, and this is the C part, that is bond enthalpy, that is the symbol we have as a delta. Bond enthalpy is H subscript here. With reference to that, chemical reaction involves the breaking and the making of the chemical bonds. Energy is required to break a bond, and energy is released when a bond is formed. It is possible to relate that of the reaction to change in energy association with the breaking and the making of chemical bonds. With reference to the enthalpy of the changes associated with the chemical bond, two different terms were used in thermodynamics, and these were the two terms, that is a bond dissociation enthalpy, bond जब dissociate होते हैं, that is the bond dissociation enthalpy, and mean bond enthalpy, where we're finding out the mean bond enthalpy, and that these were the two terms that is used in the thermodynamics here. Now we will deal with the further here. Let us discuss about that these terms with reference to the diatomic and the polyatomic molecules. These two terms, that is bond dissociation enthalpy and the mean bond enthalpy, will discuss in the two form, that is diatomic molecule and as well as polyatomic molecule here. With reference to the diatomic molecule, that we can consider diatomic molecule here, that is consider the following process in which the bond in 1 mole of dihydrogen gas, that is of H2 are broken. आपको यहाँ पे डायटोमिक में क्या हो, जो H2 है डाइहाइड्रोजन गैस है आपकी, 1 mole of डाइहाइड्रोजन गैस है, उसको हम कैसे ब्रेक करेंगे वो देखते हैं. And here we have an H2 gas and that gives 2H here, and that is of HH bond enthalpy, that is diatomic molecule, when it will change in that bond enthalpy, we can say that that is a 435.0 kilojoule mole inverse here. With respect to this, the enthalpy change involved in this process is the bond dissociation enthalpy of the HH bond and hydrogen hydrogen bond. We can say that the bond dissociation enthalpy of that change in the enthalpy, which one of the covalent bond and of a gaseous covalent compound that is broken from the product in the gaseous state. Now that it is same as that of the enthalpy of the atomization of the dihydrogen. So this is true for all the diatomic molecule. We can say that, for example, with respect to that, we have a two equation, that is a Cl2, that is in the form of the gaseous state here, and that gives a 2Cl, and this that is in form of the gaseous state, and we will get the bond enthalpy of CCl, and that it will get here is that 242 kilojoule mole inverse. And with respect to the O2, that is in the form of the gaseous state, that gives 2O here in the form of gaseous state, and that is for bond enthalpy of O or double bonded O, where H minus, that is of enthalpy here, and that is for 428 kilojoule mole inverse here. With regard of this, in this case of the polyatomic molecule, bond dissociation enthalpy is different from the different bond within the same molecule. Now we'll discuss about the polyatomic molecule here. Reference to the polyatomic molecule here, that is, let us consider a polyatomic molecule like methane. Polyatomic molecule को हम consider करते हैं like example of methane here, CH4. The overall thermochemical equation for its atomization reaction is given as CH4, that we can termed as methane, CH4 in the form of the gas state. It gives C carbon in the gas form, and 4H, that is of hydrogen in the form of the gas state. Where the bond enthalpy, we have delta of A, that is H subscript, that is 1665 kilojoule mole inverse here. With regard of this, in the methane, all the four carbon and hydrogen bond, if I'm talking about carbon and hydrogen bonds, they are identical in bond length and as well as energy. However, these energies required to break the individual carbon hydrogen bond in each of the successive states that differ. So we'll discuss that in detail here. Here CH4 that is in the form of the gaseous state, it gives a CH3 gaseous state and plus H that is of gaseous state. We have delta bond H of subscript, we will get a plus 4 to 127 kilojoule mole inverse here. Now CH3 that is in the form of the gaseous state will give CH2 that is in the form of the gaseous state plus H that is in the form of gaseous state. It gives delta bond H subscript, and that is plus 439 kilojoule mole inverse here. Now we are talking about CH2 here, that is in the form of the gaseous state here, that is that it gives CH of gas and plus H of gas here, and that is delta bond H minus that it gives equals to plus 452 kilojoule a mole inverse here. CH that is in the form of the gaseous state, it gives the carbon in the form of gases, and plus that is of H that is in the form of the gases here, and that gives delta bond H subscript, that is plus 347 kilojoule mole inverse here. Now then after that we'll break it out. पहले था CH4 फिर CH3 वो break हो गया, फिर C2 फिर CH2 फिर CH, and then it will break, and then CH2 therefore we can say that CH4 in the form of the gaseous state, it gives that is a C carbon, and that is 4H gases, that is of delta bond atomization enthalpy, that will get 1665 kilojoule mole inverse here. In such cases, if I'm talking about, we use mean bond enthalpy of carbon and hydrogen bond. For example, in CH4, that is delta CH bond of H enthalpy is calculated as delta that is of C and H bond enthalpy, and with respect to the H subscript, that is of 1/4, and that is atomization enthalpy equals to 1/2 1665. That what we will find it out here, a kilojoule mole inverse, and when we cancel it out we will get here as 416 kilojoule mole inverse. That we'll find it out with respect to the methane here. Now moving ahead, we have a formula here that we have to discuss is delta R of H subscript equals to sum of bond enthalpies, that is of reactants, minus sum of bond enthalpies, that is of product. This is the formula when you are finding out that is delta R of H subscript, that is summation, that is of sigma bond enthalpies reactant minus sigma, that is bond enthalpies of product here. Now in terms of this, we'll just talk it about the next one, that we have enthalpies of the solution symbol that we have is delta of solution H of subscript. This is the symbol here, and the enthalpies of the solution, if I'm talking about the enthalpies of the solution of a substance, is the enthalpy change when 1 mole of it dissolve in a specified amount of the solvent. जब specified amount of the solvent में अब हम substance को dissolve करते हैं, that enthalpy of that solution as infinite dilution as an enthalpy change observed or dissolving the substance on an infinite amount of that solvent when the interactions between the ions or the state molecule is negligible. Then from then for that time, particular that time, we can dissolve that. Okay, when an ionic compound dissolve in an solvent and then ions leaves theirs under that ordered position on the crystal lattice, and these were now more free in the solution, but the solvation of these ions, that we can say that the hydration in the case of the solvent of water, and that also occurs in the same time. So this is shown with diagrammatically for an ionic compound, or what we will show in the form of ABS solid here is. So this is AB, this is in the solid state, and that is of solubility of H subscript, that is equal to get A plus and an aqueous solution plus B minus in an aqueous solution here. So this AB, this is the delta that is of lattice H subscript, and that is of hybrid H subscript here in the case of the H plus here, if I'm talking about. And these, the difference is H plus A plus gaseous state plus the B minus gaseous state. With reference to that, we can say that the enthalpy of that particular solution of AB, that is of delta or that is hybrid of H subscript of the water, and therefore they determined by the selective values of the lattice enthalpy, that is of delta lattice H subscript, and the enthalpies of the hybridization of the ions, that is of delta hybrid here. And that you can see that the deltas of solubility of enthalpy, will find it out as a delta lattice of H subscript and delta hybrid of H subscript here. And for most of the ionic compound that is of delta solubility of H, that is positive, and that dissociation process of the endothermic also. and for this most of the time क्या होता है वो endothermic होता है और आपका positive value देता है. Therefore the solubility of the most salts in water increases with the rise of the temperature. If the lattice enthalpy is very high, the dissociation of the compost may not be take place at all. Why do many fluorides tend to be less soluble than the corresponding chlorides? Estimate that you can just estimate the magnitudes of the enthalpies of that made using those table we'll discuss in the enthalpies and the lattice energy, that is of enthalpies, and the bound in energies we'll discuss here. Yes. So these were the some mean single bond enthalpies in the kg mole inverse here. And with respect to that, that is hydrogen, carbon, nitrogen, oxygen, fluorine, silicon, phosphorus, and then sulfur. We have chlorine, bromine, and iodine. And with respect to that, hydrogen, chlorine, nitrogen, oxygen, fluorine, silicon, phosphorus, sulfur, chlorine, bromine, and iodine. जब हाइड्रोजन का विद रिस्पेक्ट टू हाइड्रोजन दैट इज 436, एंड कार्बन का विद रिस्पेक्ट टू हाइड्रोजन इज 412, एंड with respect to carbon itself that is 347. Nitrogen का 389 with respect to the hydrogen, with respect to 93 carbon with 293, and with nitrogen as well as that is 159. Okay, this is were the enthalpies, one enthalpies, that when nitrogen combined with a hydrogen it will be 318 in here, and when nitrogen combined with a carbon that is 293, and when nitrogen combined with oxygen that will be 159 here. Now moving ahead with the oxygen when combined with the hydrogen that is 464 here. Okay, and when oxygen combined with carbon that is 351 here, and then when oxygen is combining with nitrogen that is 201, when oxygen is combining with oxygen itself that is 138 bond enthalpies they are forming. With respect to the fluorine here, fluorine when form with hydrogen it forms a bond enthalpy is 569, and then when fluorine is formed with carbon that is 439, and when it forms with a nitrogen then it is 222 bond enthalpies, and fluorine when it formed with oxygen then it 184, and then fluorine when it formed with fluorine then of course that is 159 bond enthalpy that we will be seeing here. With respect to the silicon, the hydrogen it forms that is 293 bond enthalpy it forms, and then after that respect to the carbon silicon is formed, then the bond enthalpy is 289, and silicon with nitrogen it is not mentioned here, and it is not formed actually. Silicon and oxygen then 368, and silicon and fluorine then 540 bond enthalpy we see, and 176 with silicon and silicon as well. With respect to the phosphorus when bond enthalpy is 318, and 3264 with respect to the carbon, and 209 with a phosphor that is your with nitrogen, then 351 with oxygen, at 490 fluorine, and 203 that is with respect to silicon, and then same itself 213 bond enthalpies has been shown. For this 339 with hydrogen, 259 with carbon, and then for the nitrogen oxygen it does not form, and 327 for fluorine, and 226 is for silicon, and then 330 for the phosphorus, and then 230 for itself here. This will be the similar as you can see. Okay, next moving ahead with the chlorine here, 481 with respect to the hydrogen, hydrogen combined with then hydrogen with combined with chlorine, then with form 431, 330 with carbon, 2 bond enthalpy, and 201 will be nitrogen, 205 with oxygen, 255 when it formed with fluorine, and 260 with silicon, and 331 with phosphorus, and 251 with sulfur, and then 243 itself by the chlorine and chlorine bond enthalpy that they are forming. For the bromine 368 with hydrogen, 226 with carbon, 243 will be nitrogen, and then oxygen के साथ bromine बनता नहीं है. 197 with fluorine, 289 with silicon, 222 will be with phosphorus, 203 with 213 with sulfur, and 218 with chlorine, bromine, and chlorine, and 192 with your bromine, and with itself with bromine. The bond enthalpies has been shown. With respect to iodine, 297 with a hydrogen and 238 with carbon and nitrogen के साथ बनता नहीं है. 201 with oxygen, fluorine के साथ बनता नहीं. 213 with silicon, 213 with same with phosphorus with respect to iodine here. Then sulfur के साथ बनता नहीं. 209 with chlorine, 110 with bromine and 151 with iodine. So this is the representation of, you know, that is the sum mean single bond enthalpies in kilojoule or mole inverse here. Now moving ahead, with respect to that, we have some mean multiple bonds enthalpies. These were the, you know, single bond enthalpies, and these were the multiple bonds enthalpy. अगर single bond बन रहा है, like carbon का, you know, like for example like carbon के केस में carbon अगर hydrogen के साथ या carbon के साथ बना रहा है तो वो single bond बना रहा है, hydrogen के साथ बना रहा है तो single bond बना रहा है. तो अगर ये सारी जो combination है ये single bonded है तो इसके केस में ये इनके bond enthalpies है. But difference to that, some mean multiple अगर enthalpies बना रहा है, अगर नाइट्रोजन के साथ डबल बॉन्ड बना रहा है तो 408 उनका enthalpy होगा. वो नाइट्रोजन ट्रिपल बॉन्ड बना रहा है नाइट्रोजन के साथ तो 946 होगा. और कार्बन नाइट्रोजन के साथ अगर डबल बॉन्ड बना रहा है दैट इज 615. और कार्बन अगर ट्रिपल बॉन्ड बना रहा है नाइट्रोजन के साथ देन इट फॉर्म 891. कार्बन डबल बॉन्ड बना रहा है कार्बन के साथ 611. कार्बन ट्रिपल बॉन्ड बना रहा है कार्बन के साथ दैट इज 837. कार्बन डबल बॉन्ड बना रहा है ऑक्सीजन के साथ 741. कार्बन ट्रिपल बॉन्ड बना रहा है ऑक्सीजन के साथ दैट इज 1070 हियर. ऑक्सीजन के साथ डबल बॉन्ड बना रहा है दैट इज योर 498 हियर. ओके, so these were the possibilities, that is a sum mean multiple bond enthalpies in the kilojoule or mole inverse here. So आज के क्लास के लिए इतना ही. नेक्स्ट क्लास में हम लैटिस enthalpy को डिस्कस करेंगे. But before that we'll just had gone through with the unit 1, unit 2, unit 3 and unit 4, and even though till states of matter then we had discussed about you know unit 1 as well as unit 2 as well as unit 3 here. So unit 1 में हमने some basic concepts of chemistry पढ़ा था जिसमें हमने importance of chemistry, so natures of matters, properties of matters and their measurements, uncertainty to the measurements, laws of chemical combinations, and then we had discussed Dalton's atomic theory, atomics, molecular masses and mole concepts and molar masses, as well as the percentage composition and the stoichiometry and stoichiometry calculation that we had done here. Unit 2 means structures of atoms, subatomic particles, atomic models, developments on leading of the Bohr's models of atom, Bohr's models of hydrogen atom, towards the quantum mechanics models of the atom and quantum mechanics model of an atom. Unit 3 में हमने डिस्कस किया था classification of elements of the periodicity in the properties, that why do we need the classification, classify elements, that genesis of the periodic classification, the modern periodic table and the prevent form of the periodic table, as well as the nomenclature of the elements with the atomic number less, that is you know greater than 100, and electronic configuration of the elements of the periodic table, electronic configuration of the types of the element of S block, B block, D block and F block, and then periodic trends in the properties in element, that what we had discussed. Then we had discussed the unit 4 here, the chemical bonding and the molecular structure, where Cossell's levels approach in the chemical bonding, ionic and the electrovalent bond parameters, the valence shell electron pure repulsion, that is whisper theory, valence bond theory, hybridization, molecular orbital theory, that is MOT, bonding of some homonuclear diatomic molecule and hydrogen bonding. Then we had discussed unit 5, that is of states of matter, intermolecular forces, thermal energy, intermolecular forces versus thermal energy, the gaseous state, the laws, gases law, ideal gas equation, kinetic molecular theory of the gases, behavior of the real gases, deviations from the ideal gas behavior, as well as liquefaction of the gases in the liquid state. That's what we had discussed here. Now we had discussed starting with the unit 6, that is your thermodynamics state, application, measurements of delta U and delta H, calorimetry वो हम डिस्कस कर चुके हैं, enthalpy change, delta H of reaction जो कि हम डिस्कस कर रहे थे, enthalpies for the different types of reaction that we also discussed. उसके बाद हम lattice enthalpy, फिर spontaneity and Gibbs energy change in the equilibrium हम वो डिस्कस करेंगे. उसके बाद हम unit 7 डिस्कस करेंगे, that is of equilibrium in the physical processes, equilibrium in the chemical processes, dynamic equilibrium, law of the chemical equilibrium and the equilibrium constant, homogeneous equilibrium, heterogeneous equilibrium, application of the equilibrium constants and the relationship between the equilibrium constant K, reaction coefficient, that is Q, and the Gibbs energy, that is G, and the factors affecting the equilibrium, ionic equilibrium in solution, acid bases and the salt, ionization of the acids and the bases, buffer solution, solubility, equilibrium, and the sparingly soluble salts that we discussed here. So please, if you had not subscribed our channel, so go through with the subscribe button. Please like, share and subscribe our channel. Thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on the comment box. Please like, share and subscribe our channel. Thank you.